Good afternoon, everybody. Thank you all for coming. I am Aaron Parecki, and I am very excited today to talk to you about how to hack OAuth. I hope we have time for questions at the end. I can't promise it, so if you do have any questions, feel free to tweet me, and I will definitely answer them after the talk. And if Twitter is not your thing, I'm also on Mastodon, and you can reach me there. So I am a senior security architect at Okta, and I work on a lot of the OAuth specs themselves and work on that kind of that side of things. My background is also in web standards, both at W3C, which works on things like HTML and CSS, and then also the IETF, which is where the OAuth group is. If you've ever searched for anything online about OAuth, you've probably landed on a site that I maintain, which is OAuth.net. So if you ever see anything wrong with it, please feel free to send a pull request or file an issue because it is open source on GitHub. So we're going to talk about how to hack OAuth, and in order to do that, we're going to do a little very quick intro to what OAuth is. And if you've ever tried to learn this stuff by reading specs or looking online for information, it can kind of feel a little overwhelming at times. There's a lot to it. It's not just one spec. It can feel like trying to find your way through a maze to understand what's going on here. And that's because it's a pretty complicated subject. There's a lot to it, a lot of moving parts, and it's been around for a long time. So things have changed a lot over time as well. So instead of going through the maze in order, because I promised that would be boring, we're going to take a quick trip back in time to understand why we even have OAuth in the first place. So this used to be a very common pattern, which was a new app like Yelp would launch, and it would ask you to type in your email and the password to your email, which we see this now. We're like, why would anybody ever put in their, give their email password to a random app like Yelp or maybe like Facebook, right? Because we know now that this is a terrible idea. You shouldn't share your email login with random apps. But at the time, people were doing this all the time because they actually wanted what this application was promising, which was they actually wanted to find their friends on this network. So people were happily giving their passwords to random applications. And these companies realized that was a problem and were trying to find a way to solve that. And they were looking for a way to let applications like Yelp access this part of their account, but not also have access to the actual emails in your email account. So this was the original problem that OAuth was created to solve, which was how can we let an app access data without actually giving it your password? And this takes a bunch of different forms. So there's, Yelp might want to access your contacts, or Last.fm wants to access your listening history from Spotify, or Buffer's trying to post to your Twitter account, things like that. So it's always about getting access to an API. Some application over here accessing data over here. That's what OAuth is all about. And at the end of the day, the way this ends up working is that the application gets what's called an access token. It'll take the access token, it'll put it in an API request, and make a request to the API. Now that access token is like a key. It's basically the key to that account that represents the fact that that user approved access to this application. I like to think of it as an analogy of a hotel key card, where you check into the front desk and you give that person at the front desk your ID. They give you back this hotel key, which is like an OAuth access token. You take that key to the door and you open the door, and the door lets you in. Now, in order for this system to work, the door doesn't actually care about who you are. The door doesn't need to know your name or your ID or your credit card info or anything like that. It just needs this access token that has a little bit of data encoded in it that says this key can open the door. So this is exactly analogous to OAuth, where in OAuth an access token doesn't necessarily represent a user, it just represents access to data. So that's a really important point that we need to keep in mind as we're talking through these examples. So quick rundown of how OAuth works, because as we walk through how this works, we'll start seeing where we might want to jump in as an attacker and try to actually break the flow and get access to something we shouldn't. So in OAuth, we typically talk about these roles, where The terms in bold are the sort of like conversational terms that you would use when you're talking to coworkers. The terms underneath in parentheses are the names that you would see in the spec, which is one of the reasons that specs are really hard to read, because they always have very specific terms for these things, which are not necessarily the same language you use when you're talking about it. So in OAuth, we talk about a user who is trying to use some application. That application needs to get an access token from the OAuth server, and then the app's going to use that access token at the API. Of course, the application is being used by the user through their browser, this device. So we're going to look at how data flows back and forth between these different roles in order to make this exchange happen. So it starts out, the user opens up the browser and types in, visits the application's website, like maybe yelp.com. And the user clicks the button that says login. And that's the user saying, hey, I'm trying to use this application. The app says, great, I don't have any way to log you in right now, but you can go over to the authorization server to grant me access. That causes the user's browser to land on the OAuth server through a redirect. And then that's basically the user going over to the OAuth server saying, hey, I'm trying to use Yelp. It wants to access my contacts. The OAuth server says, cool, who are you? Please log in here. Do you allow this request? Ask permission from the user. And then if the user says yes, the OAuth server generates this one-time use temporary code, sending it back to the user's browser. And this is a really important part here, because this is actually essentially the OAuth server is trying to get this temporary code into the application, but it's doing so by sending it through the user's browser, which means this is an opportunity here where an attacker could try to jump in the middle and intercept that. So the user's browser lands back at the app and says, hey, here's the code I got from the OAuth server. You can use this code to get a token. And then the application can talk to the OAuth server from behind the scenes from its own web server and say, hey, I got this code from this user. Here's also my client secret. And please give me an access token now. And then it replies back with the access token. And now everything can continue. So you might notice that there's two different colored lines here. And this is a really important concept here in OAuth. This is the idea that the bottom lines are called back channel requests, and the top half is all front channel. This is the difference between sending data over a secure HTTPS connection versus moving data around through the user's address bar. So we're very used to sending data from a client to a server over HTTPS. So used to it, in fact, that we forget a lot of the benefits of what that provides. It has a lot of benefits, like you validate the SSL cert, so you know what server you're talking to. That connection is encrypted, so you know it can't be tampered with, and the response comes back immediately, so you know the response is valid as well. So I like to think of this as hand delivering a note, where you just walk up to somebody, you hand them a thing, you can see them, they can see you, you can see they took it, they can see who you are who's giving it to them, and it's very secure, right? You know that it's not stolen because you watched it change hands. Now, passing data via the front channel through the user's address bar is more like just throwing it over a wall. So, and this is like, it's actually it's a very accurate analogy, and you think of it from both sides of this wall, where the cat over on the left is trying to issue this temporary code over to the application, right? But all it can do is sort of just throw it up in the air and hope that the other cat catches it. Can't actually see whether or not it's been caught. And I think more importantly than someone might jump and steal it is actually that you can't tell if it's been stolen because you can't see over that wall. And then on the other side of the picture, that cat is just waiting for this this code to come flying over the wall, and something comes flying over the wall. Who knows where it's from, right? Hopefully it's from the right OAuth server, but there's no way to tell because there's that wall. So this is what it is like to send data through the user's browser, through the address bar. And that just makes it a very challenging environment to do securely, and also provides an attacker with a lot of opportunities to jump in and mess things up. So why do we use this at all? It turns out that it is actually a very critical piece in OAuth for a couple of reasons. One, it is the way that the OAuth server can actually interact with the user in a way that everything in the system can be assured that that interaction did actually take place from the user and it wasn't impersonated. And secondly, the thing receiving data doesn't need a public IP address, which is really important when you're talking about mobile phones, because a mobile phone, an app on a phone, does not have an address that a remote server can push data into. So instead, we go through the user's browser to deliver that data. So that's a very quick overview of how OAuth works. We're going to start talking about when OAuth doesn't work. And there are, it turns out, a lot of ways that you can hack OAuth. And there's so many, in fact, that they are actually pretty well documented. And they are documented in several different RFCs, both OAuth 2 core, as well as like a native app draft, as well as a special security draft. Also a new one, which is very close to being finalized, this security best current practice. And these all do a very good job of actually explaining a lot of the sort of well understood and easily solved attacks. So I'm going to let you read those later because you can just read them, and they're actually not terribly written in terms of spec language. So bookmark those links and take a look at those sections, because those talk a lot about the sort of very concrete attacks that you can prevent with some solid techniques. So instead, we're going to talk about some hacks that went wrong that turned into major press from companies that actually had some incidents blow up. And this is a demonstration of like when you do something so wrong that it turns into a complete disaster, right? So starting with Twitter. Twitter, back in 2013, had a problem with their apps. And their problem was that all of their API keys were leaked. Now, these were the headlines that were coming out. Twitter OAuth API keys were leaked, or whatever the headlines were. What actually had happened is that somebody basically just posted them all up on GitHub. And it decompiled the apps, posted the keys on GitHub, and was like, hey, look. So the end result of this was that it's not like any user data was stolen because of this, but the end result is that then anybody can now impersonate the Twitter apps, which basically means that you can perform an OAuth flow as if you were the real native Twitter app instead of a third-party Twitter app, which might do things like getting around rate limits that exist for third-party apps that don't exist for first-party apps, or maybe bypassing the approval screen that asks users for permission, things like that. So you still have to get someone to actually log into this fake app, but it is still pretty bad, and it sort of loses the whole concept of this is the real Twitter app. So what's the solution here? Basically, the solution is you can't put secrets in native apps. That's the end of the story. There's no way to do it. There's so many reasons why this doesn't work, and it was demonstrated for us a long time ago. And I wrote this blog post if you are interested in more details or need more reasons, ways to convince other people of this. So what OAuth did in response was OAuth 1 required secrets for everything. And that was clearly not a good idea because of exactly this problem. So in OAuth 2, there's actually a way to do an OAuth exchange that doesn't require a secret. And that way we can get around the fact that you can't use a secret in a mobile app because it wouldn't be secret. So, and that is called PKCE, or PKCE. So this is an extension to OAuth. It's one of those things in that maze. And this is basically a way to do an OAuth flow for applications that can't use secrets, especially like mobile apps, and now also JavaScript apps. So let's walk through this flow again and see how it changes for this kind of application. So we start out the same with the user visiting the app and saying, I'm trying to log in. Now, the app doesn't have its own secret registered, so instead it says, hang on, I'm going to generate a new secret right now and store it and then hash it. The idea with the hash is that hashing it is a one-way operation where if someone steals the hashed value, there's no way they can actually know what the original value was, right? At least not in any reasonable amount of time. So then the app says, cool, please go over to the OAuth server to grant me access, and now also take this hashed value with you. So someone at this point could steal this value, but it doesn't matter because they can't reverse engineer it. So that causes the user to go land at the OAuth server. I'm trying to log into this app. Here's the hash secret it gave me. User logs in there, approves the request, and then the server generates that temporary code again, just like before. So user then takes that temporary code back to the app. Now, again, this is the part that someone could steal. If someone's able to steal that code being thrown over the wall, well, now they can't do anything with it because there is no way they could have also stolen the secret the app made. So this back channel request now, the app says, hey, here's this code I got from the user. Here's the plaintext secret I made up. Please give me an access token. And the OAuth server says, oh, well, when I generated this code, I saw that there was this hashed value that came in. So let me go and hash this value that you're saying now in this request and see if they match. And if they match, it means that the code wasn't stolen, and it is in fact the same application making this request that started the request. So that's a pretty clever solution to sort of avoid the need for a pre-registered secret, because if it's pre-registered and shipped in a mobile app, it would no longer be secret. The good news is this is also often handled for you automatically by a library. So in the case of a native app like iOS and Android, there's AppAuth SDK, which is just like a generic OAuth client, and you can use that, and it will do this PKCE flow. Also, if you're using a native SDK from someone's API or like a product, then it'll probably be doing this as well. But it's kind of nice to know what's going on under the hood, I think. OK, second hack. JSON Web Tokens had a little incident a couple of years ago where all of a sudden everyone announced that JSON Web Tokens were vulnerable to various bypass issues. Again, it was called slightly different things in different press. This is relevant to OAuth because JSON Web Tokens are often used as access tokens, or at least in other systems, even not even OAuth, as a way to sort of authenticate requests. A JSON Web Token is a very long string which has a very specific format. So this is one way that an OAuth server can issue access tokens that look like this, and then your application will take this over, present it back to an API, and say, like, here's my access token, please process this data. And the data inside that JSON Web Token will represent things like the user who logged in, the timestamp for which it's valid. These are all called claims. It's all these little properties with key value properties. So there's things like, timestamps, which scopes were issued to the access token, things like that, right? The user account. And the idea is that this is supposed to represent, this is a way to sort of encode this data that you need in order to process the request without having to go look it up somewhere, like in a database, which is cool. It has some performance enhancements by doing that. Great. But if someone could change this data, they could then just decide to be any user in that system. So because this is actually just base64 encoded JSON data, you can go and open it up and change the values and see what happens, right? So the way that JSON Web Tokens are protected is by a signature. So that last chunk at the bottom is a signature, which is normally signed by a private key that the OAuth server uses, so that the API can use its public key to verify it. But the interesting thing about JSON Web Tokens is that that header chunk at the top actually describes what signature method was used to sign the token. So if you notice up there, it says the algorithm is RS-256, which is the asymmetric cryptography algorithm. And if you were to just go and change that value to, say, none, then that means this JSON Web Token has no signature. Now, the problem was that a lot of these libraries were essentially taking this header, saying, oh, well, depending on the value of this algorithm, I'm going to go do verification these different 5 ways. One of the ways was none, which meant no verification. So anybody could just go and change any of these values, change the header, the signature type to none, re-encode a token, and go talk to an API, and guess what? They would get in. So that's clearly bad. It turns out the fix for that is to disallow that method, right? You might think. There's another even more subtle version of this attack, which is that if you change the algorithm to a symmetric algorithm, like HS256, then the API endpoint might think it's validating the token because it'll check the signature. And what it'll do is it'll go fetch the public key of the OAuth server and then use the symmetric method of calculating signature to verify that, which means as the attacker, you can actually go fetch the public key, treat it like a secret, just a secret, pop it into the signature, generate your own signature, and now, sure enough, you're able to trick this library into validating a signature where you were able to also forge the signature. So this was really bad. Thankfully, a lot of the libraries patched it, but basically the moral of the story here is that this header is essentially it's untrusted external data. So the same way that you don't trust a form on a web page to be like user ID equals admin, you don't trust the header to have any data that you actually are going to rely on. You need to sort of whitelist your algorithms that you are expecting, only using asymmetric algorithms so that someone can't come in and forge a signature. And that's really the solution. So yeah, the header in this is untrusted data. Treat it like external input that you would sanitize and validate just like every other external input that you are dealing with. The fix that most of the libraries shipped was to essentially force you, when you're validating a token, to put in the list of algorithms you expect, which is usually just one algorithm. Maybe two different sizes of bits, but usually it's just one algorithm. And that way the library will only allow that algorithm to verify the token, and then you're fine again. So, third attack. This one's a fun one. I like this one because it's not even an attack on the protocol. It's a much harder one to solve. This was 2 years ago, almost two and a half years ago, where it was called either like a phishing email or an OAuth worm. It had a couple different names again, depending on what press you were reading about it. But what happened here was that basically like an attacker got in and was able to access a ton of Google accounts all at the same time very quickly. So let's look at actually what happened here. Do you see anything wrong with this picture? This was step one of the attack. A user would land on a screen like this. And maybe this looks fine. Like the SSL cert is valid. You're really on Google. It's clearly not like someone trying to trick you into entering a password. But what if you click the little drop down next to Google Docs and this appears? Now it's starting to look a little suspicious, right? What is docscloud.info? That's probably not Google. Also, who is this Eugene? So what happened was this attacker basically went into the Google Developer Console, registered a new application, a real OAuth client, using their developer account, called that application Google Docs, and uploaded the Google Docs logo. So you're not looking at Google Docs requesting access. You're looking at this fake application, or real application, depending how you look at it. There is an OAuth client in the system with a client ID that is requesting access to your account. Notice what permissions it's requesting. It wants to be able to manage your contacts and send email from your account. So if you think about what it can do with that, basically, if you ignore the suspicious screen here and just click allow because you were expecting to see it or something, you would grant an access token to this application, which had the permission to download your address book and then go into your Gmail account and send an email from your account. And that email that it would send an email to all your contacts. And the email said, this person has invited you to view a document on Google Docs. Open the document in Google Docs. And this is not spam because this is coming from a real Gmail account through Gmail's own API through their servers to some other Gmail account. It's a real email, so it's not getting flagged as spam, and it's going to people who already have a relationship because they're in their address book. So you click this button, open in Docs, and then you land on actually Google, which you see this. So now you're sort of already expecting to see it, so it's even less surprising. And then you click through, and then it happens again, and again, and again, and again. And you can see how quickly that would explode. So as soon as this started spreading, this all went down very quick. So it was 20 minutes before Google tweeted this out. And they were like, we're investigating something. Something's going wrong. Report the email as phishing. OK, then they finally figured it out, what was going on. And of course, the quick fix for them is just to disable that application, because they can just kill the application's access. The next time anybody clicked on that link, they would just see this error screen. So did that solve the problem? Kind of, not really, because again, there was no real hack here. It was a phishing attack, essentially, tricking users into clicking something they shouldn't have clicked. And this is a very hard problem to solve, because you have to train people to understand the security model around this, right? So the there have been some changes that Google has started doing since then, and I think this was the thing that really kicked this off. So they have started launching this new sort of user data policy around their API, and there's a lot of new guidance in there about how applications should be able to do an OAuth flow to Google. There's advice, which is actually like good advice in general for OAuth, which is things like only request permissions that your application needs, only start the OAuth flow when you actually need it, and don't just do it at the beginning. This is good advice in general for building applications. Don't just like when you open an iOS app and you get like the 5 prompts that says like, this app wants your location. Oh, we want to send you notifications. Oh, we also want your contacts, and it's like overwhelming, right? So don't do that. Instead, only request permission at the time you need it. And the same applies to OAuth as well. Don't request access to information you don't need. That's all great. One of the other things they've been doing in this is also defining what they call restricted scopes. And you might notice that these are 2 of the scopes involved in that attack, which was if an application is requesting access to your Gmail account or your Google Drive, then that falls under what they call restricted scopes, which triggers a new set of requirements to actually get your app live, including what they call a security assessment, which costs between $15,000 and $75,000, which is basically their solution to not having this problem happen anymore, right? Because now an attacker would have to spend a lot of money. The side effect of this is that it unfortunately killed a ton of applications that were legitimate, that were actually trying to be helpful to users and but would tie into their email, right? So IFT is shutting down their Gmail integration. There's various tools for email marketing or contacts, things like that. Like these tools they've made a decision where it's too expensive to go through that audit, that it's not worth it to them, and they would rather just shut down that integration, which I think is really unfortunate, because it's essentially killing the whole concept of the open web. It's no longer sort of a free playground to play in anymore, and you have to pay a lot of money to play, which is too bad. So this was sort of the fallout of that attack, and I guess this is one way to solve it. I'm not a huge fan of this way to solve it, though. There's the real problem, the real source of this problem was this approval screen did not make it clear that this was a fake application, right? So if you looked at that screen, it would say Google Docs was trying to access your account, and people would click yes. So if you look at other screens from other applications or other services, these all look very different because every service designs this screen themselves. This is GitHub's, and they do something really interesting here. I think that GitHub would be far less likely to fall under to the same attack because they do 2 important things. They say, this is the developer of the application, and they put their GitHub username on the screen, which means if someone wanted to trick a user, they would have to create a GitHub username that looked somewhat convincing to be GitHub. It's not, if they can't use GitHub, they're going to have to register some name like support or admin or help or something like that, which hopefully GitHub has blocked those usernames from being registered. So that's step 1. And then down next to that green button that user clicks on, there's a URL, which is where you're going to go redirect the user back to, which is another clue that something might be wrong. So if that had said docscloud.info or getcloud.info, probably people wouldn't click it because that looks pretty suspicious and it's clearly not GitHub they're going to go back to. So I like this approach better of like trying to help the user understand what's going on. It is a challenge, I recognize that, and Google does have a very different demographic than GitHub users, so maybe they thought through this and decided the pay-to-play was the best option. Okay, so the last attack was we're going to talk about is Facebook. This one was almost exactly a year ago. So this was the headlines were 50 million Facebook accounts were hacked. You remember that? That was pretty big news. And it made a lot of press. It both, of course, blew up in like the security internet, but also it made like major press headlines as well because it turns out Facebook is literally everywhere, and 50 million is a very big number. So people were writing all sorts of things about how, what went wrong here. One of the really interesting things I think that happened was that because it was such a big breach, Facebook actually put out a lot of information themselves about what went wrong, which is not normal when an attack like this happens. Normally, the company will put out some sort of, really, oh, we're sorry, or we fixed it, there was a problem, but now it's gone, sort of vague information. But in this case, Facebook actually published quite a lot of detail. They had their public-facing announcement that was sort of, the vague, oh, there was something and we fixed it. But then on their security blog, they also posted actual details about what went wrong. So I wanted to dig into that to take a look at that and see if we could learn anything from it. So in their own words, they said this vulnerability was the result of the interaction of 3 distinct bugs. And I think this is also a really important thing here, which is that when we start looking through these, you're going to see that each of these bugs by itself doesn't seem that bad. And maybe it would be it's clearly a bug, but it doesn't seem like anything that could lead to 50 million accounts being taken over. So it's only once you stack them that becomes a problem. So the 3 bugs. First, Facebook has this feature called View As. So if you are on your profile page and you click this little button and say View As, that's a way that you can see what your profile looks like to other people. Now, they've changed it since this happened last year. So right now, it will only look like this, which is the public. So you see that little black bar at the top. This is what your profile looks like to public. It used to be that you could click into that and see what it looks like to specific other people, which is a really cool way to validate to verify your privacy settings. So you can make sure that this post didn't appear to this particular person based on what groups they were in, all the settings of your profile. So that's a great feature. That's cool. More companies should do this. This is a very useful thing. So when this happened, that View As feature let you actually go and choose another person who could view that your profile as. This is supposed to be a read-only interface. That makes sense. You're looking at sort of your profile from the outside. There was a problem. There was, that box that appears on the top of your profile that lets you type in and upload stuff? Well, there was one version of that, which is the one that lets people wish their friends happy birthday. It incorrectly provided the opportunity to post a video. Now, this doesn't seem that bad, right? Because you're looking at your profile page, you click View As, and then the uploader appears and says, upload a video. OK, meh, not a big deal. Second bug. They launched a new version of the video uploader. And in that version, this video uploader incorrectly generated an access token that had the permissions of the Facebook mobile app. Now, this is starting to sound a little bit worse, and it's now kind of getting to the realm of OAuth. This is still, it doesn't seem like that big of a deal because at the end of the day, it's just an access token for your account, and maybe it has some extra permissions, but if you wanted to do that, you could just go use the Facebook mobile app and get the same access token, right? But the reason this is a problem is that because essentially this video uploader is supposed to be this one little mini app, and now somehow it's able to get an access token that looks like it's from a different application, the mobile app. OK, third. When the video uploader appeared as part of View As, it generated the access token not for you as the viewer, but for the user you were looking up. Now, this is starting to sound bad. This isn't something that should have ever been even possible to do, because you should never be designing a system that can sort of just swap out user IDs like this, right? So the result was that you could go use the View As feature to look at what your profile looked like to somebody else. You would get an access token that belonged to them, which had the permissions of the Facebook mobile app. So that's the complete account takeover. And as soon as you have that, then you can just rinse and repeat. So that's how it, again, just blew up into 50 million, because it's just cascading after that. So what can we learn from this? This is a tough one, because it's all about just internal application design, right? I think the real key here is that you need to stop thinking of your internal boundaries, internal network as trusted environment. Because essentially what was happening here was somebody who built this system let the video uploader request an access token and then issued an access token with the wrong user ID in it. That shouldn't have ever even been a thing that anybody thought to do. That shouldn't have ever been possible, right? Like normally, the reason we have OAuth is so that everything in the system knows that the user did in fact land at the OAuth server, logged in, saw the request, and that's how the access token got issued, because the user was involved. So make sure you're treating these components of your apps the same way you would treat third-party apps, and don't let applications pretend to be other users, because even though you might think, oh, well, it's fine, it's our application, we're not going to do anything wrong. Well, it turns out that you might do something wrong, and if you do, and if it gets stacked on top of other bugs, then things can turn into major press headlines that you really don't want to see for your own company. So on that note, that is the end of my presentation. I hope you learned something. I have a book available on OAuth where I talk about this kind of thing in a lot more detail. And I have one copy with me. And I would love to give it away to somebody. So the way we'll do this is tweet something at me, mention something you like about OAuth, and then at the end of the day, I will pick a random winner, and I will give you the book. So I'll track you down here. Thank you all very much for coming, and I hope you enjoy the rest of the day.